who backs up Gilson Engineering here in Western Pennsylvania and West Virginia. And Adam Ellis is the technical specialist, and Adam is actually online with us from the UK this morning, from England, or it's for this afternoon for him, from England, and he is the technical specialist, and he will be leading most of the presentation. Together, Adam and Greg have over 40 years experience in the field, and so I think this presentation should be very informative. So if you guys are ready to go, you should all see Adam's screen, and I will mute and turn it over to the Fluke folks.
Okay, thanks, Jeff. Hi, everyone. Yep, my name is Adam Ellis. I'm based in the UK. I run our technical support team. We've got a small global team covering probably about 20 hours in the day of technical support online via our ticket system or by email or phone. As Jeff said, I've been in the company for about 20 years. I've worked in service, calibration, and sales, and now technical support. So we'll give you a general run through of the technology and break into some applications as we go. We'll try to pause, I guess, probably every 10 minutes or so in case there are any questions. If you can put those in via the chat box, that would be great. And right, let's get started. Just get to my slide. Okay, right. What is infrared? It's simply part of the electromagnetic spectrum. For us, or for everybody, it exists between the visible spectrum and radio waves. Scientifically, infrared extends up past what we're describing here as 20 microns. But typically for industrial infrared temperature measurement sensors, we class them as nominally typically 1 micron up to 20. Generally, we stop at about 14 micron. But we go from what we call short wave up to long wave devices. The radiation's due to movement of molecules, and luckily for us, certainly as we approach the visible, we've got many times a lot more energy in the infrared than in the visible. Some of our sensors, where they approach the visible part of the spectrum, we just at the lowest end of what we make covers just about the yellow and the red, and our eyes typically are measuring between 0.4 and 0.8 micron, and it's for that reason we can use glass optics in some of our devices. We're measuring fairly close to what the eye measures. Moving on, but our sensors themselves aren't intelligent in the sense that they're essentially just passive receivers, and what they collect is emitted energy. Some of the energy passes through the environment, so we can be sensitive to that. All devices have a detector of some sorts. There's different technology for that, and we're guiding the energy to the detector by means of windows and optics. They can be plastic, glass, crystal type of components, but we're purely passive. If you ever see a laser or an LED from the sensor, that's purely a guide to where we measure. We're not shining anything out to receive something back. Then we have a bunch of gain and linearization electronics, and all of our devices fixed. Some have a display on the sensors themselves. Others don't have any kind of display, but they all give an output to either a secondary display or a control system. Typically, milliamps, millivolts, thermocouple used to be the most common. Then we moved into ASCII over serial, but we now can interface directly with PLCs, Rockwell, Ethernet IP, Siemens, and GE for Profinet. Some of our PC-based systems will also output via OPC directly to a PLC. Why use infrared? There's some good reasons to do it. Many times we have applications where we're replacing thermocouples, but generally infrared's used where other technologies can't succeed, essentially. So very fast measurements. Some of our devices can measure in milliseconds. Some of our line scanning devices actually have response times in microseconds. We're also able to measure moving objects, which means we can measure them as they pass, or we can track them. So we're able to, with line scanning devices or panning motors, we can actually track devices so they appear static. Difficult to reach. That may be in terms of physically hard to get at. So it could be a discrete object inside a machine, for example, or something inside an atmosphere that's dangerous. Hot objects. Well, I mean, hot objects are not necessarily from 1700 degrees centigrade, but especially with thermocouples, they don't tend to last long above 1700 degrees, or may be impossible to measure. So we're able to measure, in some cases, up to 3000 degrees Celsius. A lot of our applications as a company tend to have sanitary requirements that can be food safe or contamination risk. We're able to measure, because we measure everything without touching it, we're able to measure things without contaminating them. So we also have applications in food and chemical. We have applications in chemical storage where to physically touch the chemical could cause a dangerous reaction. And we touch into medical at lower temperatures for manufacturing of pharmaceuticals. The last comment, a profile needed. When people need a profile, they tend to need many measurements in a very short period of time to be able to create a profile line of temperature over a product. And that's more or less impossible to do with contact means. So we were able to scan something and create a profile line many times a second. And you can only really do that if you're not touching something. We make devices with many different wavelengths. Part of this is due to the availability of detectors in the open market. There are only a handful of detector manufacturers globally, and they make detectors according to windows that you get in transmission in the air, but also typically optimized to where certain surfaces, because we typically only measure a surface. There are some applications where we can measure subsurface to a very small amount or to a greater amount, but generally we choose wavelengths because that's where we can sample the most energy and get the most repeatable reading. And there are some aspects where we choose wavelengths where we avoid things like flame, and we're able to measure thin things without seeing through them. But generally, the wavelength is optimized to the application. One of our main considerations, and this is probably why certain detectors are available, is that you have some windows through the air essentially, and that air can be dry air or moist air. We have to consider moisture and oxygen and nitrogen. If we were to make detectors, or if detectors were available, and detectors are available for weather metrology, if we were to use those in industry, we would find that we would have a change in temperature according to the distance from the sensor to the object, and that's something that no general industrial device can really work with, because we have no active way of determining distance. So we choose wavelengths where the air really has no effect. And this next slide shows each color band is a typical region where we make sensors where we just have windows to look through. In the case of the biggest area, F, luckily we've got a big window over a broad spectrum that allows us to make devices and everybody else in low temperature. And we also have a window that allows us nicely to measure the temperature of glass here. And then as we move further down, it's windows where we can measure metals and thin plastics. The other things that we sometimes have to consider is how we can measure or how we can look through certain materials. So we know in thin plastic applications that we have a couple of very short, narrow bands where we can measure, in this example, polyethylene. So we make specific sensors for plastics with what we call a notch filter, so very specific to the application. With glass is also interesting in that sometimes we need to measure glass. So where the transmission is lowest, here we can measure glass in process. Other times we may need to look through glass. So if we're looking into a vacuum chamber, we have to consider devices where actually glass has good transmission, and we measure through it. There are other examples when, for example, quartz glass is very hot and glowing. We can measure into it with infrared. It's a bit like a non-contact dip probe. But generally, glass, we either want to measure it or we want to measure through it, and we use quartz glass as optical elements in our devices. Quick pause for questions. I'm not able to see the chat. Greg, I guess we've got no questions so far.
Well, I've got one here that's you can start with. It says, if I understand correctly, you have to pick a unit with the correct wavelength based on the temperature and the material, correct?
Yes. Yeah. In a nutshell, when we advise on applications, quite often the first defining question is, what's the nominal temperature? Then we talk about the span of temperatures. Sometimes we talk about what's your must-have temperature range and what's your nice to have. That helps us to define, if you like, the basic possibility of different devices. Then when we go to material, that then really helps us to hone in on the wavelength. But yeah, absolutely right.
All right. And there is one more I see here that might be a little ahead of some of the things we've described, that in terms of devices that would address this, but I think it's worth addressing, especially since it's a timely question right now. It says, do you have a device that can alarm if it sees any individual entering a plant that has a temperature in excess of 99 or 99.5 degrees Fahrenheit?
Yes, we do. in terms of a device capturing a temperature and giving an alarm, yes, we have thermal cameras and scanners that can do that. In terms of purely detecting the temperature, not thinking about what it means, yeah, that's quite easy to do. There are some caveats to that. If it's human body temperature, which we can advise on. Our devices typically are not FDA approved, so our ability to promote them as human temperature solutions, we're not allowed to do that. What we can do is advise you on best practice in order to get the most reliable reading, and that would be in terms of placement of a device, how the subject is brought into the field of view, what functions you have for offsetting according to varying external temperatures. And the other thing is that they're only ever a first line. Even FDA approved infrared devices tend to be approved if they supplement a second measurement. But yeah, short answer, yes, we can do that easily.
Thanks, that's all I have for now.
Okay, all right, very good. Okay, so Planck's law. Every infrared temperature manufacturer is subject to Planck's law. It makes things in some ways very easy. It can add confusion sometimes, but generally, the general part about Planck's law is it helps us to characterize the output from the detectors that we use in how we build up essentially our energy to temperature conversion in our devices. And we observe Planck's law because it really defines everything we do. If we take the blue line, the light blue line, if you can see that, for example, that shows us that there is energy, usable energy, from about 6, 7, 8 microns up to 100 microns. That's in pure physics. The peak wavelength at room temperature is 10 microns. And so you might often see thermal cameras, low temperature sensors defined as 8 to 14 micron devices. They have a center point, typically around 11 microns, and they can measure down to -50 Celsius. They can also measure up to 1,000 Celsius. If we take for another example where we have 1 micron, where we make sensors specifically for the metals market, if we take the energy at 1 micron at 500 degrees, and then we see the amount of energy that we get on the 1,000 degrees Celsius line, we see that we've got 1,000 times more energy at 1,000 degrees than we have at 500, and that's how we use that to characterize the devices we build according to these laws. When we're looking at any given application, we tend to work with Wien's displacement law, and that basically tells us that for a given temperature, there's a peak wavelength, and the peak wavelength roughly conforms to this blue line. What it means generally for industrial sensors is that as there's so much more energy at short wave compared to long wave, we tend to typically always look to specifying the shortest wavelength possible. That gives us the ability to have the best repeatability, independent from accuracy. That allows us to have the best repeatability and the least variation when we have unknown surfaces. Within that, the challenges that may not allow us to use 1 micron are things like transmission and reflection and the material. But we're all governed by and restricted by physics. Let's go to the next slide. Okay, so there's some terms in infrared that you might hear or might have heard. you may hear black body, you may hear grey body, and you may hear non-grey body, or essentially a real body. At the moment, we're just talking about something that's opaque, so nothing transmitted. So metal, wood, textiles, coal, carbon. What we receive in terms of emissivity, a black body itself will emit everything and absorb everything, but it will reflect nothing. We use essentially as close as you can possibly get to a black body, and they're often described as reference sources are often described as black bodies, even though strictly speaking they're grey bodies, but black body is good enough. What we have in the real world as a non-grey body or a real body is we receive emitted energy, but we also often have to consider reflected energy, and that really in most applications that tends to be, I wouldn't say the biggest challenge, but it's one of the biggest factors. But we also know a lot about emissivity based on materials testing and data that's been gathered over the years, and also with our own experience. If you then add transmission into the mix, we've got reflected energy, we've got emitted energy, and we've also got potentially transmitted energy. Now, transmitted energy we have to consider sometimes in thin film plastics or glass or ceramic type applications. The main point of this really is that the sensor receives everything, really doesn't know what it's receiving. Everything reflected, emitted and transmitted all add up to one. Within our devices, we're able to tell our sensors and scanners and cameras what the ambient temperature is. We generally assume that the temperature inside the device is the ambient temperature. That's an assumption. We also are able to input into the sensor what the emission factor is. Emissivity is a standard parameter. We're also able to tell the sensor what the transmission factor is, and that's not necessarily the transmission of the object. In an application, if we consider transmission, we often need to avoid that. We don't necessarily want to measure what's behind here. Transmission for us applies to our optical system, but also if you have a secondary optic or window in terms of a protection window or looking into an oven, sometimes we can use it to apply gain in a kind of field calibration sense. If you have to work with dirty or scratched windows in between repairs, but the sensor can take into account all of these in how it calculates its temperature. The biggest challenge is to know what they all are and have the means to get that information into the sensor. The basic rule of thumb is if we always seek to maximize emissivity, the effect of reflection can be reduced almost to nothing. And nothing really means within the specification of the unit. Once we get outside of that, then we really have to start considering a little bit more sophistication about what's going on. But that's kind of standard work for us. That's what we do. There aren't so many surprises. It's also why it's always good to, if possible, to see an application so we can give you advice. Emissivity. Now that's our most common compensation factor. In the top example, we've got our black body. Inside the sensor, we would set an emissivity of 1. The black body is at 1,000 degrees. for the example, we call it 1,000 energy units, and the sensor would read 1,000. That's in the perfect ideal. A real object is less than that, and in this example, the real object is only emitting 10% of its temperature as infrared compared to a black body. The sensor has got an emissivity of 1, and the reading in general cases would be 100 degrees. There's a whole wavelength temperature analysis that on some devices would mean that wouldn't be 100, but generally as a rule of thumb, 90% loss of energy, 90% loss of reading. That there's a wavelength argument, and that tends to be mostly for low temperature units. But if you were then to change the compensation setting in the sensor to 0.1 to match the 10% emission, so 10% emission, 0.1 emissivity, you can then correct the reading to be essentially to be true. There's other challenges with reading something that really is only 10% emissive, because it's also 90% reflective. That's a whole webinar. But as a rule of thumb, that's what emissivity is about. So let's take a pause there for questions. Greg?
Yes, I see a couple of them here. We've got one says, how close do you need to get to the object? And does the accuracy improve the closer you are?
You don't need to be close to an object to measure it. There is a very small loss in energy as a function of distance. We already minimize that because we're looking through the air. It tends to be the further you are away, the larger the spot size that you measure, and that gives you essentially more. That keeps your kind of watts per square meter constant. So you don't get any improvement by being close up. Where you can improve repeatability is using the unit at its focus point. You can use it out of focus. It doesn't mean the reading will drop off. It just means that's essentially where your spot size is sharpest. It doesn't improve the accuracy, but it does mean that you can rely on the fact that you know where you're measuring from. There's an inverse to that, is if you do get too close to an object and it's very hot, you can influence the reading in terms of heating up the detector and causing thermal shock in the unit. And then there are some applications where you can essentially increase emissivity by using gold reflectors, but you have to then be very close. But generally, no, you don't need to be close. There's no improvement from being close up.
All right, thanks. One more. It says, first off, is calibration required yearly?
I would say that 85–90% of devices that we receive for calibration, as long as the optics are clean, not scratched, and the sensors hasn't been overheated, never need to be adjusted. There's a very small consideration in a sensor's device for the first year in terms of detector aging, but that's all taken care of in our standard accuracy specification. It's often advised, if you've got applications that are fairly rugged, and it can be possibly that we receive a sensor. We always give before and after values, and it may be that we receive the sensor with a dirty lens, we report on as found, and we make a correction and send it back. Sometimes calibration is as much as a maintenance, but purely as a device in terms of its own drift in ideal situations, you don't need to calibrate them. They don't drift and have to be offset and gain adjusted every year. they're very stable in that sense. But generally, annual is what we recommend, and if it's after 1 or 2 years that you see that the as returned is the same as found with no action, a lot of people extend that to 2 years, because then they're satisfied that the environment the sensor sits in doesn't have any influence on calibration in terms of it's nearly always optical contamination. So yes, we recommend it, but it's not a must-have. It often depends on your quality manual, essentially.
Yeah, I would add that a lot of people who own these pyrometers, even a very high-end one, don't calibrate on a regular basis, and I think the reason is that a user's ability to know the emissivity of the target and the effects of things like background temperature and perhaps the transmissivity of windows that you're looking through, generally those things specific to the application can add more uncertainty into your measurement than does the drift of the instrument, which is usually smaller.
Mm-hmm. Electrically, they're very stable.
Yes, that's right. Let me ask one more question that I see here in the chat. It says, does gas being present affect your temperature reading, and if so, how?
Generally, no. Our detectors keep away from gas bands. There's a very small when we calibrate devices for the glass industry, one part of the spectrum does slightly touch a CO2 band. So when we're calibrating them, our Cal Lab considers some environmental things, but generally, no, it's not something that you need to think about. If you've got a device, for example, let's say you've got one of our line scanners on a rotary kiln, there's usually 100 feet or so in between the kiln and the scanner. And a common question that we have is, okay, what about weather effects? Is that going to affect the reading? On that particular device, the wavelength is optimized to give us the best path through atmosphere at different humidities. So we get no effect on that. In general, general purpose low temperature sensors, we're also only touching CO2 at the very long wave. So generally no effect. So day to day with the average sensor, it's not something that we need to consider. If you've got an application where you're looking into a gas, generally if it's an inert gas, it's not so important. But if it's some kind of reactor, we may need to look at the absorption band of a specific gas and make sure that we specify a sensor that's away from that absorption band. Okay. Last part to that. Generally, if there was gas and it was an influence, you would see it as an attenuation of the reading, unless the gas was significantly hotter than the object. And we have sensors that are actually optimized for measuring gas. So we're able to measure hot CO2 and hot NOx, hot carbon dioxide. But generally, something would attenuate the reading, if at all. All right.
Okay. That's all for questions at the moment.
Thank you. All right, let's go to the next one. Okay, types of sensors. The first standard type of sensor is, I guess, traditionally called a pyrometer, but pyrometers tend to be more aligned to the high temperature industry. But infrared thermometer, spot sensor, pyrometer, they all essentially mean the same thing. We measure a temperature typically based on the average of the energy over a certain area with a single detector. Our spot size is a function of distance, but it's defined by what we call a distance to spot size ratio. So for example, a 100-to-1 device at 50 inches is half an inch, but it may be easier to think that if it were focused at 100 inches, it would be 1 inch. So it's purely a ratio. If you've got a device that's focused to infinity, it's typically, whatever the distance it is, divide by 100. So 200 inches away, 2 inches. We make devices from 2 to 1, which would give you essentially a very big spot at a given distance, right up to 300 to 1 in spot sensors, and in line scanners and cameras, an equivalency of 570, 600 to 1. It would tend to be that the more expensive a sensor is, the better this D2S performance is, and that's generally because our higher range of sensors has multi-element glass optics and typically a longer optical channel. When we go down to lower cost sensors, this is a mid-price sensor, we typically go up to 70 to 1, and that's because we've got a smaller optics and a smaller body, and the units that are 2 to 1 are really tiny, you know, the size of your thumb. They've got a small lens and they're very short. Sometimes you can choose a unit with 100 to 1, and you might choose to have the focus point very close. And what that would allow you to do is to, when you get past the focal point, your spot size starts to get bigger. Sometimes, depending on the application, you might want to measure quite a large area, but you might have a high temperature device which forces you to a high D2S. If we take a device and we focus it close up, we give ourselves a large area at distance. But it more or less means we can, with a spot sensor, we can really match the optics with different options that we have according to the application. The next main technology that we have is a line scanner, often referred to as a scanning pyrometer. This takes a single detector, which would be in this device, would be up here looking down, and then we have a rotating mirror, and we're able to scan from left to right or right to left and build up a thermal image very quickly and very accurately, very repeatably. Having one detector measuring every spot really allows us to accurately see relative difference, but also it's only one sensor that needs calibrating. Every rotation it self-calibrates. The limitation with a line scanner is that it tends to need a moving process because it's building up the image line by line. And in an application like this is a continuous caster. This image wouldn't refresh many times a second like you might see with a camera, but the line will build by scrolling, and scrolling, and then it would appear to be moving, but it's actually being built up line by line. Line scanners are very good in that we have optimized wavelengths for specific known applications, and we can mix and match scanners and software really according to the application. Lastly, we've got thermal imaging cameras, sometimes referred to as FPA cameras, focal plane array. It's a two-dimensional image. The resolution in terms of pixels is quite similar to a line scanner, but because we're taking a two-dimensional image, we're refreshing that complete image up to 60 times a second. In our camera, for 60 Hertz, we're actually able to support 60 Hertz is a refresh rate, and we're able to actually support that refresh rate by having a very fast array, which is actually faster than the refresh rate. So we can really give 60 measurements of 640 by 480 pixels 60 times a second. The limitation, or in terms of the physical difference or the spectral difference, is that our thermal imaging camera is what we describe as a long wave general purpose camera. Can be used for food, certain plastics, textiles, wood, asphalt. Can be used in metals with certain considerations regarding the point in the process. Generally, if you've got an application where you've got a decent amount of the metal in the air, it builds up an oxide layer. So it can be used in the steel industry too. And a camera gives I guess a huge amount of flexibility in terms of allowing you really to visualize the process, think thermally. I often use a camera if I'm making an application evaluation or investigation. But yeah, great device, very flexible software, Ethernet IP, Profinet, lots of flexibility with the camera. And I think, yep, so that's my part. So any last questions before I hand over to Greg?
I don't see any new ones there, Adam, so I'll try to share my screen.
Oh, no, there is one coming in. Is that similar to the FLIR camera? In a word, yes. All thermal imaging FPA type cameras of that type, so what we're talking about is 8 to 14 micron general purpose. We're all using the same core technology, which is tends to be a Vox coated bolometer. The difference between manufacturers are typically either where they get their engines from or whether they make them in-house. And there are some differences physically in designs in terms of optical quality. I know that with our camera, our front lens has a significant amount of anti-reflection coating. So that if I were to heat the front lens up with a hairdryer, there's almost no influence. And I did that on a test at home. We were looking at human temperature and the effects of the camera being outside. The other difference tends to be what's bundled with the cameras. So we have a off-the-shelf software that can run a process, and other companies have similar. It's a matter of finding something that fits. But yeah, essentially, yeah, it's the same technology. Can the thermal imager be used to detect if a vessel wall is disappearing? We use these quite a lot on if it's based on the next slide, ladle monitoring, torpedo car monitoring, kiln shell monitoring. Yes, by looking at the outside of a shell of anything, we can often infer what's happening inside, if that's what the question is. So yes, but just to remember that for us and every other manufacturer, we're measuring a surface, and it's inferring what's going on underneath that you use it for. But yes, I believe you could. It's a standard application for us in these pictures that you can see, as well as rotary kilns. But Greg can talk a bit more than that. So great, thank you very much. I'll hand over to Greg.
All right, thanks, Adam. And yeah, those thermal imagers come in a temperature range up to about 1200 C or 2200 F about. And so that gives you an idea of kind of what kind of applications they could go into and what kind of surfaces you could read. So my name is Greg Secord. I'm the regional sales manager for the Northeast states for the IR products for Fluke Process Instruments. And only recently that territory has been changed and expanded to include Western Pennsylvania and West Virginia. So a lot of you, I may have spoken with a few of you here, but in general, this is a new audience for me, and I'm looking forward to working with you guys as soon as I can. Also, newly working with the Gilson engineering sales team and looking really forward to working with that group as well. So, so thanks guys for having us. I'm going to go through kind of a real high level introduction to the kind of applications that our IR sensors could get used in. You'll recognize some of them in your own industries and your own facilities here, and perhaps are used to using infrared pyrometers in those already. Hopefully you'll come up with a few new ideas here. I know Fluke Process Instruments, our team intends to run some additional webinars in the next couple weeks and months that are a little bit more specific about optimizing your instruments in these applications and getting a little more in depth for one industry or another. So we'll try to make sure you guys get an invitation to those. The first slide here is about primary metals, and certainly metals in general is one area where we find probably the most common uses for pyrometers. Due to the high temperatures involved, it's really advantageous to have a measurement method that doesn't have to come in contact with the material. And when we refer to primary metals, we're really talking about casting, or all of the upstream processes that go into creating a molten product and then creating cast bulk materials out of it. You know, those applications can range from a tiny crucible of a precious metal inside of, say, an induction furnace to a really large scale steel plant, which most of you probably have a little more exposure to. And in those plants, you have really pyrometers and other infrared sensors in lots of different temperature dependent regions of the plant. Some of the images you see here, I'll go through what you're looking at. On the left, you have an image looking through a window or a viewport into a vacuum furnace that has a super alloy material molten inside there. It's a aluminum alloy with additives intended for aircraft use. And you know, in general, in a vacuum furnace application, you have extremely clean product and very few impurities, and that's the purpose of doing it in a vacuum. But I positioned the sensor to look toward the edge there and see some of the particulate on top there, a little bit of slag on the material. Interestingly, this image is captured not by a camera, but by the pyrometer itself. Our endurance series pyrometers, the high temperature ones usually used for metals, actually have a video sighting capability. And the intention there is for you to be able to aim at your process or sight as well as you can, even through remote means. But you can also monitor the process using that video feature. You can capture video onto the computer, you can capture still shots, and that's what I was able to do here. So it's a pretty clear picture when you have a nice bright and focused target to look at like that one. On the right, you have a copper continuous casting furnace, and you have a small pool coming out of the bottom of the furnace, and then kind of the continuous cast line going through the floor here. What we used in this case was a fiber optic sensor to get this measurement. And with the fiber optic sensor, you have the detector and the electronics kind of located safely away from the high temperatures involved. You know, we did have a gas flame torch pointing right at that cast line. And so extremely hot temperatures in this area. And so if you use a fiber optic sensor, you have just a simple optical head with no electronics inside it. You're able to get that very close to the pool that you're measuring and get that measurement well with it. What that company had been doing up to that point is using just thermocouples dipped into that pool to get the measurement. And of course, one of the troubles with that is that they nearly had to replace the thermocouple each time it was used. And so it adds up over time to be quite an expensive way to do it. And we got, you know, very good matching of readings between the infrared reading and the thermocouple reading in this case. You know, all you really have to do is make sure you have a good moving fluid with enough mixture so that the surface temperature matches well with what's under it, and you can do that measurement through infrared quite well. What we've been running into, and Adam referred to this more recently, is even in the steel industries, making use of that general purpose thermal imager, and that's for looking at the outside of these transport vehicles and containers like ladles and torpedo cars. And just like the question was asked, the intention here is looking for weak spots, cracks, wear of the refractory material, so that you don't suffer a breakout or some damage to the torpedo car, and you service it in time before it becomes a hazard. All right, moving on to secondary metals. So downstream of that casting, we have lots of different high temperature processes used in forming the metals, and one of the most common ones we run into is rolling mills, of course. So with the rolling application, we're going to first start out usually with a preheat, or sometimes if it's in the same facility as casting, you'd call it a reheat oven, where big slabs of material would come into this oven and spend some time in there to get up to the temperature needed before rolling. Generally, this measurement of the soaking material is done through thermocouples that are placed inside that reheat oven or reheat furnace. But you can use pyrometers in that application, and one of the advantages there is you could really get the temperature of the actual material, not just the surrounding oven, and make sure that you truly have the temperature that you think you have. And then more commonly at the exit of that oven, and before we go into the rolling process, we'll have either a pyrometer to capture a single temperature, or to get a full profile, which you can do either during rolling or prior to rolling. And you can see in this kind of inset here what kind of profile image you'd get out of a scanner, you know, looking at whether you have cold edges or if you have streaks from the rolling process or what. Some of the characteristics of this kind of application are that you always have some cooling water or cooling liquid involved, and you generally have to look through some steam or water and water on top of the product as it's going in and out of rolling. And so it's very common to use a two-color pyrometer, which is able to kind of look through essentially that steam and still get a good surface temperature measurement. One interesting thing I was a part of recently is that working at an aluminum rolling mill, where you have product going back and forth in a reciprocal rolling operation like you see here, but whereas steel is bright red and hot, even white hot when it's elevated temperature, steel is much duller and really doesn't take on the bright appearance when it's as hot. And so one of the challenges that the company had is that as that material came through and they were looking through that curtain of steam, they were unable to see the material until it emerged from there, and they wanted to get an earlier indication of when it comes through to see if there was any bending or turning up of that material. And we were able to use a thermal imager to capture a view of that material probably a second or a couple seconds earlier than they would have been able to do by the naked eye. And it essentially appeared in a thermal image to look just like this, where you see a bright red hot material coming out, whereas the normal view of the operator looking from the control room, he wasn't able to see it until much later. So it provided kind of an extra edge in safety and ability to control that by using the thermal image. Okay, a few more of those forming applications that you'll see is both hot stamping and forging. And in both of these cases, you'll have the material being worked, whether it's a sheet metal or a bigger chunk, sometimes a round or shaped chunk being forged. These will have to be preheated, and it's pretty important to the users to make sure that they are at the right temperature before you go through the operation, so you don't end up with cracking and other flaws in the material. It's very common to have a kind of a robotic process, but sometimes it's a manual process to move the material from where it's preheated to where it's actually worked. And it's very helpful to have kind of a go and no-go indication of whether that material is at the right temperature or high enough temperature or not before you start that operation. In some cases too, you may have heated dies being used on that stamping operation, and those can be monitored as well, either with a thermal imager or with a pyrometer. In this lower right-hand view, you actually see an endurance pyrometer located pretty far away from the forging operation that's going on there. And in this case, we were able to get, despite being halfway across the room, we were able to get just about an inch or so spot size over at the part, looking near the bottom as it was rotated and being worked. But what the customer ended up doing instead is using one of those fiber optic units, and he was able to position that fiber optic unit right inside this forging machine, where it could take the nastier environment and keep the electronics safely away. All right, so moving on, another common industry, as Adam referred to, is glass measurements made with pyrometers. And really in the glass industry, you kind of have a similar scenario to metals, where you do have kind of a primary glass and a secondary glass, where you do in fact have molten glass being made into sheets through these furnaces and then a cooling layer. And you commonly have either line scanners or pyrometers in that application. Now, in almost all these cases, it's advantageous to use a 5-micron device, whether it's a pyrometer or scanner, so that you're not looking through the glass. You know, you saw where glass is highly transmissive when you go to the lower wavelengths, but if you're up at around 5 microns, you can start seeing the surface of the glass instead. And in some cases with very, very thin glass, there's even another wavelength at 7.9, almost 8 microns, where it's common to use that. What you see on the left here is a window having come through a tempering furnace and out and passing under a line scanner. And so you can kind of tell from the shape of that window that this is an automotive application. It's pretty commonly done with both flat architectural glass and with automotive glass. But what you'll generally do is position that scanner in just a couple inches gap that you have between that tempering furnace and at the outlet of that, you'll have kind of an air quench that happens very quickly after that. And in that very thin gap between those two components, it might just be a couple of inches, you can have that line scanner look right down the middle, and as the product passes underneath, as Adam described, you have many passes of that pyrometer going across and scanning and then creating a 2D image for the user of the actual temperature profile. In this case, the customer had broken it down into 3 different zones, which is something that the software can do for you. So you can set specific limits on one zone or another on what kind of temperature it should be at. Also within the glass industry, you have even small glassware, which sometimes is, say, medical syringes or other vials and things that are used in the life sciences industries and medical and scientific industries. A lot of different applications for making those measurements, either for cutting off. Generally, this starts off as a long kind of tube stock of glassware cut into small vials and then formed into what it needs to be. And in some cases, you have purification processes in the end, which are also heat dependent. And we have some thermal imagers being used in those applications to ensure that they reach a sufficient temperature to achieve purity and such. I think it's probably a good time to stop now to see if we have any questions. I don't know if any questions have come in.
Yep, there's one question. I'm just going to check that. So would a line scanner have benefits over spot sensor in rolling mill?
Well, I mean, Adam, you could address this as well, but I think the key advantage of the line scanner is simply that you get many more points across the sheet or the slab that you're rolling. And so instead of just simply knowing if you have a temperature that's favorable for the process, you can also get information about the profile, like is it cooler at the edges and hotter in the middle? Do you have uniformity issues and things like that? Do you have anything to add with that, Adam?
Yeah, there's a couple of, I mean, it depends what kind of mill you've got, but quite often, at least in Europe, the line scanners mounted in between each roller. There's a couple of things line scanning software can do, as well as just making more measurements, is we have the ability in our software to automatically track a changing width, which means if you want to analyze center left, center right, left and right, we can apply sectors or measurement points that actually track automatically either for different recipes or changing widths, but essentially auto track. Some applications may have 3 sensors, one middle, one on each side. The line scanner gives you an advantage in the fact that it's only got one detector. So really the difference is a kind of absolute. You don't need to consider really the specification of 3 different devices. that they're allowed essentially to vary by 0.3% plus a digit. And if you've got really tight control, that can be useful. The other thing is you can actually visualize what's going on. So if you can not only measure temperature, but you'll be able to see what's happening with the surface in terms of scale buildup or anything like that. So yeah, they're definite advantage. They're a higher price. They're often not so much more expensive than three spot sensors. And quite often the big benefit is the installation cost. You've only got one device to install and maintain. So yeah, good question. Thanks.
Yeah, very often with line scanners and also with thermal emitters, if you're using those in a process, you usually have an HMI or a computer screen nearby the operation where the operator can really get a visual on that temperature profile as they're operating. Just from their experience with the process, they can tell what looks good and what looks bad pretty quickly.
Yeah. Next question. Does a line scanner work well with round material? Round is kind of interesting if by that you mean you're measuring a surface that essentially curves away from you at the edges. If you were looking at a big like a bolt or a cylinder, they can do. It really depends on the orientation, and a lot of that is defined by what's the angle to the surface at that given measurement point. So they can do. I think it's a good discussion to get into separately. We can really go into some specifics. If you'd like to do that, we could follow up after. Thank you.
Okay, is that it for now?
That's it for now, yeah.
All right, thanks. All right, so I'm going to move on to plastics and the chemical industry. A lot of times these two overlap and could be one or another at the same time. Sometimes when you say chemicals, we're referring to really advanced engineered materials that come out as some sort of a polymer. And particularly extruded materials, sometimes means a bulk product. Like for bulk plastics, they're often extruded out in kind of a long strand, then cooled and then cut into pellets that can then be melted and used in any kind of process after that. But also extrusions come very often in a form that's kind of a long sheet or web material, and this is something that we get involved in really frequently. One application here is shown, both in terms of the output that you would get from a line scanner, looking at a web process, and I think it's instructive to kind of look at what this process or what this really looks like when you're trying to make that measurement. So in the bottom view of this web process, you see kind of a faint red light line. That's the laser line coming out of the scanner, and the scanner uses that laser to help you sight exactly where you're making that measurement at. And so it's making a profile temperature line of many points across this laser. And what's a little bit hard to see in this application is that in addition to the material that's running down below that's very easy to see, you actually have a clear web, which is most likely an extruded, maybe a polyethylene or some other polymer coming out of an extrusion die here and coming down and meeting up with that substrate material and essentially being laminated on top of it. And what's pretty difficult to do with many wavelengths, but can be done quite well, as explained by Adam on that one slide, using the right wavelength, and we do have scanners in, say, a 3.4 micron format, that scanner would actually read not through this and look at the background temperature of whatever's behind it, but actually look at the surface temperature of that thin material even without peering through it. And again, that same wavelength is commonly used in, say, a blown film application. Here you see plastic being vertically extruded as a blown film, and then it will be sort of collapsed and turned into either paper bags or something like a Reynolds wrap or saran wrap or something like that. In many of these applications, you're using those 3.43 micron sensors so you can not see through or avoid transmitting through that thin material. In some of these plants, you'd have a need for hazardous class designations, And so we do have some of these sensors offered in an intrinsically safe option so that you could operate in an environment like that. When you have a need for something that is not offered in that way, sometimes we can offer you an enclosure or help create an enclosure so that you can operate in that kind of environment. Paper is another big industry for us, and there are upstream and downstream processes here, but in the downstream actual paper making, you have again kind of a web material coming out, in this case much more opaque, and so you can use more of a general purpose wavelength to measure it. But what you see on the left here is a thermal imager measurement of kind of a thick specialty paper. And in this case, what we observed was that they had cooling water going into the rolls. This paper was just coming out of a drying process right upstream of here, and it had passed over some cooling rolls. And in those cooling rolls, the water flow was restricted on the one side, where it was flowing successfully on the other side, is what the company found. But what it led to very quickly downstream is that you have a big difference in temperature on the right side versus the left side. And that's borne out extremely easily by grabbing that profile with a thermal imager. These processes, by the way, are moving quite fast too, and they're still able to be captured pretty well. Certainly with a scanner, which operates at a very high speed, but even with a thermal imager, you can do a good job of it. And both of these are thermal imager images. On the right side, we have sort of similar to what we looked to on the last page, but this is a paper product that then has an extruded plastic layer laminated onto it. And the concern of the customer here is to get the thickness of that laminated layer as uniform as possible across that sheet. And while they're doing a pretty good job of it here, they're within a range. They definitely have room for adjustment. And what they'll do is make manual adjustments to the die bolts upstream here to maintain that and avoid having big differences from one spot to another. This particular customer uses a line scanner regularly, and we tested a thermal imager, and I believe they're going to use a thermal imager on other lines going forward, because they were able to pick out those differences even with better resolution in this case. This line also employs some specific direct thickness measurements using totally different technology. But one thing we're able to learn from the customer is we're able to infer the thickness of the material because it's extruded out at a much higher temperature, about 600 degrees Fahrenheit. And so when it's applied and goes over a cooling roll, even after that point, and it comes by where the imager is, you still have a big difference in temperature, a higher temperature where the material is a little bit thicker, and a cooler temperature measured where the material is thinner. And so this gives them a proxy very quickly for the thickness that they're laying down across that substrate. All right, certainly also part of the paper industry and other industries as well is the use of large rotary kilns. And so, in the paper mill, that would be a lime kiln, but you also have these rotary kilns, and we're talking about a direct fired rotary kiln with usually a gas fired flame going down the middle of it. In the cement industry, also in other chemical production and carbon production, you would have some pretty similar kilns. With these, Adam referred to this already, but in the image on the right, you see here a mounted line scanner. That line scanner is inside of a protective enclosure for outdoor use, and that would be looking at that kiln shell temperature across the length of it. And what you'd produce is a profile and kind of an image on the software, like you see here on the left. Even the 2D image is available on that software. And the purpose of this, and I talked to a customer just this week who had experienced at their plant that did not have a line scanner like this. They experienced a big problem in January where they were missing some of the refractory bricks. That breaks down on the inside, and they do periodic maintenance to inspect it and make sure that's in place. But in their case, they didn't have any early warning that this was taking place, and they were missing refractory in one spot and were overheating the kiln shell and ended up warping that kiln shell, which obviously can be a really expensive problem. So the goal mostly here is to make sure that you're protecting that kiln shell and that you don't have problems with your refractory. We also offer different tools like pyrometers that can look into the end of the kiln and get temperatures of the actual burning zone and flame temperature, wall temperature more directly. But in general, that's kiln shell temperature is the primary measurement. All right, and there are applications, and Adam referred to this as well, where we're directly measuring the temperature of a flame. And in fact, what we're doing when we're measuring a combustion or flame temperature, we're really measuring gas temperatures. And so we have sensors that are using wavelengths that are focused on picking up the temperature of common combustion gases. So CO2, carbon monoxide, and NOx. These would generally be filtered to operate and measure a temperature somewhere between 4 and 5 microns, specific narrow bands in there that pick up those gases in particular. And this allows us to actually make temperature measurements of the boiler itself, stack flares, the flue gas temperature as it comes up out of a furnace or a boiler. And in these cases, primarily the goal is to make sure that you have efficient combustion and that you're not emitting, that you don't have emissions that are beyond the regulations that these plants have. In a similar application, we looked with a thermal imager. In this particular application, we were pretty far back here. We were about 400 feet away, we estimated, from this stack flare. The goal in this case, using a thermal imager, was not so much to know the temperature of that flame, but to make sure that we had the presence of flame in the right spots. And that was these two pilot lights. There's actually 3 in total on here, but we could see 2 of them from the angle that we were at. And we were able to zoom right in onto those spots where the pilots were and make sure that they had an elevated temperature as they should. And the risk here, and granted these systems, the flares generally come with a thermocouple-based system to ensure that they're on and to make sure that these plants don't suffer an event where they exhaust too much and can get fined. But those systems, since they are based on thermocouples, they can fail at times when the thermocouple fails, and it's not that easy to quickly get out there and replace them and do the maintenance at that elevated site. So having a backup system based on infrared was valuable to this customer so that they can make sure that those pilots were ignited the entire time. And interestingly, it looks like we're looking at a bright flame in a night sky, but in fact, that temperature on the left is just a simple iPhone picture of that same thing while we were making the measurements. You can hardly see that flame exists. It's nearly clear, and you have a bright background there. So it's something that's really hard to perceive with the naked eye, but easy to pick up with a thermal camera. There are a lot of other cases where you essentially have the same thing. You want to make sure that you know and can put safety switches into your system based on the presence of either a pilot flame or a flame curtain or something else that ensures combustion of flammable gases. And so when you're not so much concerned with the temperature of the flame but want to just make sure that you sense it's present or not present, it starts to give you a little bit more flexibility on which wavelengths you can use. So there are a lot of different pyrometer types that can be used in order to pick up at least some elevated temperature when that flame is present, and then the lower temperature when it's not present. All right, as we spend more time working with our new thermal imager product and software, we've gotten much more into critical asset monitoring applications. And in this case, you might be talking about big, essential machinery in your plant, like rotating machinery, either pumps or compressors, or in the case here shown at the right, it's actually a motor that's driving a big mixer in part of an operation. Or in some cases, you're talking about electrical utility power transformers or even isolated phase bus components. In these cases, you may need to put the thermal imager into an outdoor enclosure, or even to use a pan and tilt mechanism like you see here. This looks like a little robot device, but it's actually our new pan and tilt enclosure, and this allows you to get a field of view much wider and much more specific to different locations with a single camera. So it can pan back and forth and stop at specific locations that are controlled remotely and set up in the software. And you can record several different locations over time with that pan and tilt mechanism. This one actually is an embedded video, so I'll give you a quick look at what that looks like. In this case, we were specifically focusing on one area that has a bearing that is known by the operators here to heat up over time. So they wanted to look specifically at this area and see if it experiences heat up. And also we were tracking the hottest spot in this particular area, which we see got over a little bit over 100 degrees Fahrenheit. In this application, this was operating inside of a very hazardous atmosphere. And so any heat up, any excessive heat up of any of these components could create a really deadly and risky situation. So it was important to have this monitoring full time, whereas they didn't have it in place before. But in addition, we were able to put this imager inside of a purged enclosure, which allowed it to operate inside that environment safely. Okay, another one related to fire and safety here is just simple fire prevention. And you know, our device, and this is again a thermal imager application, but it's not really a flame detector, so to speak, but in most of these applications, the application really calls for what we call hotspot detection. So large piles of coal going into a fossil plant or even now biomass sometimes can experience some self-heating, and hotspots can develop that, of course, could develop into a fire situation. And so catching those ahead of time by means of a surface measurement is something that can either catch something that's already caught fire or maybe is about to catch fire. And again, using a pan and tilt mechanism with a camera can allow you to monitor a very large yard, perhaps with just one imager or two. In this application, I'll get the cursor again. In this application, we were at a biomass plant, which was using wood chips, just like you see here, brought in by a conveyor, put into a large hopper, and then using big screw presses, they moved that material down into the boiler. And the problem they experienced is that these wood chips sometimes, especially due to the friction from that screw press, would sometimes catch fire in a place that they shouldn't, which of course results in a fire situation and a shutdown of the plant and an inefficient situation. So they were looking for a means to monitor that. And you know, this hopper was a big, dark room where you couldn't really see anything looking into there, but with the thermal imager, you get a much different view. You have a distinct difference in temperature between some of the chips coming in and the others, and you could really easily catch a hotspot before it develops into something dangerous. On the left here, we have an actual scene from a CNC machining operation in a wood mill. This particular mill had at least 12 of these CNC machines operating at a time, and they were machining wood out for products, and of course creating a whole bunch of sawdust. And I'll show you quickly, this is another embedded video. Sorry about that I can run. But you can see as this mill moves around and machines out that part, we were able to trace the hottest part in the view, which of course is what had just recently been milled out. And based on the programming of that CNC machine, at times if they create a pause in one location that's a little bit too long, what they found was they'll get excessive heating, and sometimes they'll actually start a small fire. Actually, it happens pretty commonly, they said. And this particular plant had experienced a really big fire not so long ago, and they were looking for an automatic solution. You know, at this time they're using operators to detect such things and hurry up with some water to put that flame out, but obviously that wasn't successful for them. So getting some automatic monitoring in place was important for them. And really, we've heard from a lot of lumber mills and places where, you know, in the exhaust system you have a lot of sawdust moving in a situation where any spark could be a problem. So and it's not just bulk piles and operations like that, but finished material coming from things like rubber tires, fiberglass insulation, anything that generally has a varying density of the material as it comes out of the process. it's sometimes when you come out of a heated process, if you have lumps that are higher density than other parts of the material, those can end up being hotter during a drying and storage period afterward and start smoldering and become a fire risk. And so in a lot of applications like that, we've been able to help people with fire detection or really hotspot detection solutions. I think we'll open it up to questions again, but before we do that, I just wanted to mention while this slide is up that what you see here is a few of the brands that are folded into what we call Fluke Process Instruments. So Fluke Process Instruments is a small group within the greater Fluke Corporation. I'm sure you're familiar with Fluke from the handheld test tools that they make, but our portion of the company is really made up of legacy companies and brands, especially in IR, that you may know and may have products from already, called Raytech and Ircon. Those brands and those companies have been part of Fluke for a couple of decades already, so nothing really has changed there other than in the last few years we've decided to brand our new products that replace these legacy ones as Fluke Process Instruments. So the newer products have this logo on them. And our sister company or sister group within the companies is DataPack. DataPack is they make thermocouple-based profiling systems for things like temperature studies on heat treating furnaces and such. That's not part of what Gilson